Thanks so much. It's great to be here. I don't think I've ever been invited to go long before. That's very exciting. I did not cleverly prepare for it the way Adrian did, sadly, but I will just take my time in talking about my slides. So, indeed, I'm going to talk about drip magmatism. And the first 3/4 of this talk, even though I'm showing a picture of Venus here to be provocative about talking about planets and indeed about exoplanets, what I want to do is talk about some new data that actually demonstrates drip magmatism as an important process on the Earth. I think that one of the things that we need to do as planetary scientists is make sure that we're well grounded in what we can actually measure and confirm on our Earth and kind of use that as a starting point. And so that's really what this talk is about, and then I'll talk about planets right at the end. All right, so back in 1991, K&K from Cornell were in the Altiplano in South America, and they suggested this model by which a thickened lithosphere might drip downward, and here they're kind of showing the pre-dripping and then the beginning of the dripping here. Perhaps the crust is involved too, that the lower lithosphere could be lost in a ductile instability looking very much like a drop, sinking down into the mantle, and then causing the surface observables that they had motivated them to make up this model, things like uplift and high heat flow, and the most interesting part to me, these strange magmas that erupt in places that are not plate boundaries, and they're very often high in potassium or sodium, or very high in volatiles, water and carbon, and so unexpected and sort of unexplained by normal plate tectonic theory. And I got very interested in this years ago in my graduate career, and began to think about it. And so this is our more maybe detailed model of what might be happening. So at the top you see in blue what would be considered the plate, the lithosphere, and here is a dripping instability. It creates an annulus of high topography around itself, formed briefly, but ductile flow really prevents making an arching bottom of the lithosphere, and so that kind of idea really doesn't work very well if it's a ductile process. It really ends up largely flat. Sometimes if there are lots of drips you can thin the lithosphere a little bit, but you're not going to get that big arch into which the asthenosphere is going to rush. And so when you're running numerical models, that kind of takes away one of the melting mechanisms that had been proposed. So before I continue through this slide, let me point out what's important about this and why we would be interested in studying it. Because if you can understand a process that creates magmatism away from plate boundaries on the Earth, then it's something you can apply to one-plate planets like Venus and Mars, and that you can look at as a process in the early Earth. And so that's where we started, just looking at it in numerical models and trying to understand what effects would and wouldn't be caused by this process in terms of surface observables, and in fact seeing if we could find another explanation for why magma would be produced by this process when in fact it doesn't create an arch in the lower lithosphere into which hot asthenosphere floods, thereby melting adiabatically. When you look at them numerically, you see that doesn't happen. And so the question is, where do the magmas come from, and can we in fact apply this to other planets as a general process that would happen away from any plate tectonic boundaries or in the total absence of plate tectonics? And so the dense material begins to sink. Here we're imagining that it's in fact a density anomaly that causes the sinking. It's been proposed shortening and thickening of the lithosphere can do it. Previous melt injection by a previous melting event can make the material dense. Some density anomaly is going to drive this. Now, Herrig et al., 2010, they suggested that between drips, so if you could imagine this as periodic with another drip over here, another drip over here, that between the drips, in fact, there's a possibility for a stress state that would allow any magmas in the asthenosphere to escape upward between drips. And so that's another potential process to consider here. But here what we're going to consider is what we see at the bottom. There can be a little bit of adiabatic melting in these little bits of this annulus of high topography that appears briefly, but we don't think that's the major way that melting can occur. We think that what happens is that as this material sinks, particularly if it has been metasomatized or otherwise enriched by previous melts, that material is actually heating. It's virtually a sphere that's sinking slowly into the asthenosphere because it's still connected by a neck to the lithosphere, and the hot asthenosphere crowds around this sphere and can heat it up from its cool lithospheric temperatures. And if it's the right composition, it can actually melt. You can actually melt the drip itself. And you can get damp melting or metasomatism of the asthenosphere around it, as well as damp melting or metasomatism of this delaminating lithosphere as it sinks, and devolatilization. So that's the kind of thing that we investigated. Let me show you in a little bit more detail what it is that actually happens. And so here is a graph that shows pressure on the vertical axis, pressure going downward into the Earth as if it were an Earth section, and temperature on the horizontal axis going across. And here I show a series of solidi for different compositions. In other words, if you take material that's dry peridotite on this side of the solidus and you move it to the other side, it will begin to melt. And the same for peridotite with a little bit of water in it, a little bit more water, something that's water saturated, maybe some eclogite. These are potential compositions that could be in that drip that are heating up. And so if you run the numerical models and you track the temperature inside the drips, what you find is that in the beginning, as they're forming, they actually heat quite effectively. In a lot of cases, a temperature might start here, and then it heats up as it begins to sink, and then it sinks quite quickly. But you can see that these materials can actually heat up faster than they go down, and they can cross their solidus and produce melt. And so our model suggested that this orange area here is where melting could occur, and the black dots there are the pressure and temperature that have been inferred from the compositions of these magmas where they appear around the world today. And so we thought this was a nice correlation and suggestive that perhaps this was a mechanism that worked. But frankly, you know, and this has been nicely articulated by Deanna and by Adrian, that of course, you know, correlation is not causation, and these are models that are not fully, you know, realistic, and so we take this all with a grain of salt, and it was a nice study at the time. But here's the part that I really wanted to present today. That very rapidly people figured out a way to test this, bless their hearts, and so this was something that was suggested by Holbing and Grove the year that we published this, that you could actually test for the pressure of melting by measuring the compositions of these magmas, by looking at their normative olivine content, the composition of the magma. And if that olivine content was low, that was a relatively low pressure of melting. And if the content was high, you would have a high pressure of melting. And the chromium content of the lavas that result are similarly a proxy for extent of melting, from low extent of melting at low chromium to high extent of melting. Now, the thing that's novel about this process is that melting progresses as the drip sinks. And so as the drip sinks, melting goes to higher and higher extents. And there's really not another process on Earth where you get that kind of process. Most melting is adiabatic decompression melting at mid-ocean ridges, where melting extent goes up as pressure goes down. And so a drip magmatism would have this trend, and adiabatic decompression would have that trend. And so indeed, am I missing a slide? Oh, okay. Can we go back one then? Sorry. I went doing this in a different order than I remembered in my head. So I applied this to the young magmas in the Sierra Nevada, because this is one of the locations this has been suggested. There are these beautiful lavas that have erupted up onto the top of the Sierra Nevadan batholith. They're kind of like chocolate frosting on the top of the white cake of the batholith. And it's a bit unexpected because it's after subduction had ended. And so it's long been suggested by others than myself that dripping had occurred under the Sierra Nevada, and that those magmas could be the result of drip magmatism. And so indeed that works. And so here's olivine on the vertical axis and chromium on the horizontal. And this is the beautiful positively correlated trend of these young lavas from the Sierra Nevada. And you can see that Loihi Seamount in Hawaii, the 90 East Ridge, and Kamchatka, and the Galapagos, which are down here, do not follow that positive trend. And so this is a tectonic-specific case. And so this new data, which is unpublished, joins the work that's been done already. And so Holbig and Grove, who came up with the olivine and chromium schema, applied this to Tibet and concluded that many of the lavas that were erupted from these strange isolated volcanoes in Tibet were produced through drip melting. And then Mihai Ducia, just in 2013, applied a different schema, a manganese, iron, and zinc schema, to lavas in the Altiplano, and similarly concluded that our model was correct, and that those altiplano lavas were produced by drip melting, where melt extent increased as the drip went down. And now we have this data from the Sierra Nevada and finally from the East African Rift. Parts of the East African Rift have magmas that were not produced by plumes, and they're consistent with drip magmatism. And so to me, this was very exciting because it's some degree of confirmation that, in fact, this is a way to make volatile-rich, potassium and sodium-rich magmas on the surface, lavas on the surface, in the absence of plate tectonics. And so that gives us, I think, a very good justification for applying this to other planets, now that we've actually gone some degree toward verifying it on the Earth, understanding the mechanism and demonstrating that in some places this is occurring, and in other places you can demonstrate that it is not. And so finally, I want to talk about applications to other planets. And first, I want to go to Venus. Sue Smakar and people working with the Virtus team in 2010 looked at the emissivity of lavas on Venus, and they found, and I should say I was also on this paper, really talking about compositions. I'm not an expert in emissivity or how you use the orbital data. I was a bit player on this, but demonstrating that there's very good evidence that some of the lava flows on Venus are relatively unweathered and therefore young, so they hadn't reacted extensively with the sulfur-rich atmosphere and changed their emissivity. And those young lavas occur in places that seem to be tectonically active. And so that, along with evidence that's come in recent years of young volcanism on Mars and also young volcanism on the Moon, which I can scarcely believe, but it's very exciting to think that could be possible. Drip magmatism is a way these things could be happening on planets that don't visibly have plate tectonics. Venus, this is a contentious issue. Does it have something like plate tectonics or does it not? You know, until we really get robotic boots on the ground, so to speak, or much better orbital data, I don't think we're going to be able to resolve that. But it's tempting to think that this process could apply to these planets where, unexpectedly, we do have young volcanism. And so then finally, I want to talk about results of a paper that's just come out this year. Brad Foley is a postdoc at Carnegie DTM. And I and Dave Bercovici are the co-authors. And what Brad was looking at was onset of plate tectonics after a magma ocean stage. And he's really looking at the effects of both a hotter than current Earth mantle and a hotter than current Earth surface temperature on healing faults, because you really need to be able to have persistent surface faults in a surface brittle zone in order to produce plates that can move and subduct. And this is work that Dave Bercovici has worked on for many years. And Brad has taken it up to look at the very early processes on Earth and also perhaps apply to other planets. And so what you're looking at here is plate velocity on the vertical axis versus mantle temperature on the horizontal axis. And the three lines in color are surface temperature lines. And the point is that when the temperatures are very high, they heal the faults before they can really become established plates. And what Brad concludes, now this bottom green line is a line that is pertinent for Venus's surface temperature, and you can see there's a tremendous amount of plate healing going on and very little in the possibility of plate tectonics, maybe very sluggish plate tectonics, but what his models imply is that they wouldn't be more than a fraction of a centimeter per year, probably not maintainable. And so we suggest that something that's like drip magmatism, is a much more likely process on Venus today, in between any episodic resurfacing events similar to what Adrian was talking about. And similarly, Brad looked at the first several 100 million years of the Earth after a putative final magma ocean stage, and he found that something that he calls proto-plate tectonics would occur within 100 million years of the freezing of the magma ocean, so very, very early on. And in this kind of proto-plate tectonics regime, there would be diffuse plate boundaries, and the material that was going down would really go down in the form of big drips. And so it's highly pertinent to look at those drips because they indeed could produce volatile-rich melts that would erupt onto the surface and provide new lava for reaction with the atmosphere and a quick drawdown of carbon. And so even in that pre-plate tectonic regime, even pre-episodic resurfacing regime, there is the chance for both atmospheric mediation through lava weathering and I would add, importantly, recycling of volatiles into the mantle. And so we haven't gotten to the level that Adrian is at, actually looking at the possible climate circumstances that could result from dripping and how much dripping we would expect. But I think that it is reasonable to say that there could be a climate effect of this process. We would expect this process both in the first 100 million years after a planet forms, so very early on, and on one-plate planets today. And it could, in fact, have some kind of climate stabilizing effect and give us also more hope of seeing life on rocky exoplanets, although I would certainly agree they're more likely to be bacteria than Carl Sagan in that case. But there could be this effect. And I think that the evidence we find on Earth is very good motivation for considering this both on very early planets and on other planets. Thank you very much.
We have plenty of time for questions, and surely that was a very stimulating talk that we have some questions for. So,
hey, Ben.
Hello. So it seems like a prerequisite for getting significant melting during drip magmatism is having something that's prehydrated, and so that when it dehydrates, you can get magmatism. And plate tectonics is very good at providing focus regions of hydration, so it makes sense on the Earth. But I'm wondering how that sort of necessity for volatiles would play into something like drip magmatism on Venus or the Moon, considerably more dehydrated bodies.
That's right. That's right. But so I really have two answers for that. One is that it doesn't have to be water. It has to be any incompatible element. So it could be carbon, and it could indeed be even sulfur. It could be fluorine. It could be the potassium and sodium. You know, there are many different ways to make that rock easier to melt. And so one way that that material can be placed into the lithosphere on any planet is through melting of plumes, for example, and it's proposed by, for example, Smrekar and Stofan that there are as many as 10 plumes on Venus. And since Venus's crust really consists of previous basaltic lava flows, you know, presumably all the way down, piled up, there's every reason to think that its lower lithosphere would be both enriched in incompatible elements and also unstable. And so then the other thing to think about in that scenario is that I think that all of us who have worked on magma ocean solidification scenarios agree that you can't fully dry out the interior of a planet. And so you're going to have some degree of incompatible elements in there to begin with. You don't need plate tectonics to put water in the mantle. There's going to be some water there already, and also carbon. And so a question that many of us struggle with is how much carbon and how much water and how much of these other incompatible elements is there inside of Venus today? And I don't see any way to have completely dried it out. It's just, I think as we all know, thermodynamically very difficult to perfectly dry anything. And since there's evidence in the Venusian atmosphere for loss of something like an ocean over some somewhat indeterminate period of time, presumably Venus is also still degassing.
Hey, lady, nice talk.
Hey, thanks.
I have a question about the emissivity data, mostly the interpretation. I guess the age of the flow. So Venus, because of the greenhouse effect, there's no meridional temperature gradient to drive wind at the surface, so the rate of mechanical weathering is basically zero. So how do you conclude that the flows are recent?
Well, so we're assuming chemical weathering entirely, and we're comparing the effects of a fresh basalt flow to one that has weathered largely with sulfur. And so this is data that comes from Jorn Helbert's lab looking at what the emissivity of the pre- and post-weathered material is that we've been considering. And there is not a good age constraint. You know, there isn't. And if you talk to different authors of the paper, they might prefer different numbers, but there are many orders of magnitude. I think the most conservative is to say not older than some millions of years old, or perhaps tens of millions of years old. So the relative recent. And then others are more, of our authors are more confident.
So I guess related to that is the rate of chemical weathering still depends on how fast you deliver atmosphere to the surface.
Sure.
So, the old Bullock and Grinspoon calculations leave impurities in the atmosphere for the age of the surface because of that. So just wondering how they came up with that.
Yeah,
weathering rate?
I can't unfortunately address that exact problem about atmospheric recirculation. I wish that I could, but I don't have a good answer for that. I would just only suggest that also at those temperatures, any bits of reaction would go quickly. But I think that it adds to the potential error bars of the equation. I think what it doesn't take away is that there's an emissivity difference that's most likely explained by weathering, and what it does change is the error bars on the age determination. Yeah. All right. Thank you very much.
Thanks, Christy.